Okay, so we're gonna continue multiple DTR. So recall that in the previous class, we only consider the identification assumptions, right? Now we are in a position to how we actually compute all the distribution. So solve the problem basically. So the observation. So this is the observation. So the baseline, and then A1, and then X2, A2, XK, AK, Y. And then X1 is just a given, but it actually, so A1 depends on X1, right? I mean, could be, right? And X2 depends on A1. And also, of course, this way. I mean, not really. So basically, we have some kind of a sequential, right? Sequential, effect. So, and then there's a realization, and then the potential outcome using this star notation. So basically, this is the what I would get, what we would get under this choice, right? Under this particular regime, then we basically this D bar will determine A, right? Determine A based on the history. And then for that, if we, so what would be the potential outcome for this particular regime? So that is the what we are interested in. So this is kind of our scientific question, right? But this is our reality. So these are two, there's a gap, right? So our goal is to identify the distribution of the potential outcomes on the any given D from the distribution of the observed data. So because we want to use the observed data and to characterize and then use that to solve our problem. So this is very actually I found it. Anyway, so this problem was first found by James Robbins, and then it becomes a very hot after that. But it took some time to figure out for others to understand. Anyway, so this is the main result. So the main result is that under the identification assumptions, right? Under the three identification assumptions, the joint density of the potential outcomes. So whatever the distribution of this guy is our parameter of interest, right? We can write our causal parameter as a function of this potential outcome random variables, right? But what we are interested, so this is what you are interested in. But what we like to utilize is this relationship. So basically, the joint density of this potential outcome can be sequentially expressed as the observed ones. So you have X1 and X2 given X1 and A1, and so forth. So this bar, remember, this bar is up to K minus 1, right? So this is all from X1 to all this time. So then these are basically, so these conditional expectations, I mean, the conditional properties are all, written in terms of the observed random variables, right? Observed data. So conceptually, we should be able to, so if this is correct, then we should be able to identify, estimate our causal parameter. Okay, so let's try to understand how we can actually, what does that actually mean for the simpler case, K equal 2, but the generalization should be the same idea. It's more complex. I mean, right? Maybe the notation and things like more complicated, but the essential idea should be the same. So then for k equal 2, we have so basically we have a x1 from x1 to x2, and then y star, right? So then this guy, so from x1 to x2, x2 star, we use a1. So we have a potential outcome. And then this one is actually it's a1 and a2, right? Okay, so the potential outcome, so basically we have a, so then this is a joint density, right? This is joint density, and then these are the conditional, right? These are the conditionals. So joint density is factorized into the margin of x1 and then conditional and conditional. That's straightforward, probability, right? But interesting result is that this guy, right? This guy can be written equivalently written as the conditional distribution. So this is the left side is the potential outcome distribution, while the right side is the observed data, right? Your observation conditional distribution. So then if this is correct, then that's good, right? And also another one. So this guy, same story. So this is the conditional distribution of the potential outcome of y given x1 and potential outcome of x2, which is essentially expressed in terms of the observed outcomes given x and a, given the choice of the options. Okay, so these two basically gives the so let me before I prove it, let me go all the way to this graph. I mean, graph to show some illustration of the idea. Okay. So basically, you start with x1, right? So in the baseline, you just observe x1, right? Then you maybe want to make a decision based on x1, right? Then basically you have it's like a some kind of a two paths, but you cannot really go two paths simultaneously, right? You have to choose one of the so and then you reflect yourself. What would be, right? If I choose the front path, then what would be my outcome would be something like that. So that's very interesting. So anyway, this is basically you have a two paths, right? A1 equal to, so this one is just choosing A1 equal to 1, while this one is the choosing A1 equal to 0. So for this choice, you will basically obtain, potentially have two possible options, right? Two possible outcomes. So two possible outcomes for x2. And then next step is basically using the realized, right? Using whatever the path, you will use that information to make another decision, right? So there will be another decision. So that will branch out. And then basically for each, and then you actually, in this case, you end up having four possible potential outcomes of y, because you have a two. Binary choice, first k equal 1, binary choice for k equal 2, and so you have a four possible. So then each individual will only choose one path, right? Each individual will choose one path, but the data may have several different paths, right? So that you basically can figure out. So basically, you can factorize right? Factorize the joint density into several components, and then each one you have a way to estimate it from the data. So that is the basic idea. So basically, as long as you factorize, right? As long as you factorize the joint density into several conditional sequentially, and then you know that each component can be estimated from the observed data. So that is the very nice idea, right? And I heard that when James Robbins first come up with this idea, nobody would believe that he solved the problem. I mean, a lot of criticism. And actually, Professor Danny Pepperman yesterday told me in personal conversation that when he first developed the informative sampling, people resisted because that's not realistic. but in practice, informative sampling is actually the more general, right? And non-informative sampling is actually very special. But when he first, find out this kind of argument, then there's a high resistance. So I think if you are really come up with a novel idea, then people usually resist. So anyway, so here's okay. So let's first prove equation 2. So how to prove? So we'll just start with the 2, the right side. Okay. So the right side is this one. And then let's introduce potential outcome random variable x2 star a1. So here you have already three random variables, right? Here you have 3 random variables already, but let's introduce one more. Okay, which is x2. So this is one more random variable, right? So you have a 1, 2, 3 random variable, and then one more. But you want to basically, this is the very straightforward, probability theory, right? You basically you can write it as something like, suppose you have a y, x, right? And then this is basically what this is about is y, x and z given x, dz. So this is kind of so the argument here is essentially this one, right? So, and then, right? So basically this one plays the role of z here, right? So this guy, it plays the role of z. And then I integrate out over z. Okay, now the sequential random, so basically sequential randomness assumption is ignorable assumption, right? Sequentially ignorable. Okay, maybe I should. So why SRA? So SRA is actually what? SRA is basically your x2 star a1 and is a1 given x1, right? So that basically means your oops. Oops, what am I doing? Sorry. Right? That is the basically SRA, ignorability assumption. But what we are interested in is to showing this equality. So this is the left side of 4 is x probability x2 2 star A1 given x1 A1 equals given x1 divided by probability A given x1. This is a Bayes theorem, right? So Bayes theorem says this is the conditional, joint, marginal, right? And so this is Bayes, and then we want to basically use this relationship to here. Okay, so if you use that, you can multiply. So it becomes a factorized, right? Factorized, and then so that actually, and then so you get very nice. Okay, so that's good. And then one more step, final step is we want to cancel. And in order to cancel this, we need the positivity assumption, right? So that basically proves. So proves 4, right? So basically proves 4, which basically means that we can what? We can take care of, so this is equal to this, right? This is this one. And so that we can write this way. Put it here. And then the first term, what about the first term? The first term is basically as long as you know what x2 star and A, right? If you know x2 star and A, you know x2 with a certainty, right? So that's basically this one. So basically, you know x1 A1 and you know x2 star A1. So that means you basically this value will be just this value, right? So then this guy is equal to this one, which is this one. So then you integrate out over this. So you put it to here and move it to here and integrate out over x2 star. That actually becomes proves the equation 2. Okay.
Explain equation 5 and little
I'm sorry, where?
That's good.
I see. Okay, sure. So this is the basically conditional density of x2, right? Given all this, right? Given x2. So what is the x? By the way, what is the x2? X2 is basically we know that it is x2 star 1i a1 equal to 1 or x2 star 0i a2 a1 equal to 0, right? So that means conditional on this is constant. So we know that with certainty there is no randomness error, additional randomness, right? That is basically Stuba means. Stuba means there's no additional noise comes in. As long as you know the potential outcome and you know the choice, then you know the out, right? Realize the outcome without any error. So that's basically this, because we know, so we know that this guy potential outcome of the x2 star a1 for a capital A1 equal to small a1 is x2 star. Okay. So that basically take care of the equation 2. And so hopefully we can use the very similar idea to prove equation 3, right? So that's basically just if you look at compare the proof of the equation 2 and proof of the equation 3, exactly the same structure, right? The only thing different is the corresponding random variable, which is random, but everything else is essentially the same. So basically, we wanna introduce the basically expression. Use this expression, right? So so this combined multiplied becomes a joint density of y and y star, and then you take the integration out over y star, then it becomes a marginal y. And then same thing. So this guy second term is this one, and then we first use Bayes, right? Bayes theorem to write the joint. So joint of the x, y, and a2 given x. Maybe I should yeah. Maybe I can just be prove this one more time rigorously. So proof. So basically, so we'll just use a simple notation, something like this. X bar to A bar 2 equals. So sequential randomization, no, not yet. So Bayes theorem, right? Bayes theorem. I think it's like this actually. Because we are doing sequentially. So the notation x bar 2 is x1 and x2, right? And A bar 2 is A1, A2. But we're gonna apply. So this one itself is a base, right? We don't. So this one does not use any assumption at this point. Just the base, but then the sequential ignorability assumption. So this is basically sequential SRA or sequential ignorability assumption is that potential outcome is factorized. And then positivity will take care of the cancellation. Okay. So that basically take care of proves the equation 6, and then equation 7 is the same story, right? Stuba, the meaning of Stuba is that as long as you know the potential outcome and the choice of the option, then you know the observed data without error.
So when you define X2 bar, that
Okay.
involve A1.
X, that's right. That's right. So X, that you are absolutely right. So this one is actually a potential outcome of 1 and the indicator of A1 equal to 1 plus something like that.
No, I mean the notation at X2 bar. X2 bar includes X1 and A1, right? So so then you do not need to give it A1 because you have already given X2 bar.
I see. I see. Yeah. I think you are right. We don't really. Let me check what we used in the previous note class. So this is the kind of SRA assumption. So we do use.
It does not include A.
So this is A2, then this is X bar A1, right?
X one is the function of A1. X2 bar is not the function of A1.
X
D is the function of X1.
X2 actually is a function of A1 because X2 is a realized one where X2 star is the potential outcome.
Yeah, but in your equation 6, you do not have A1.
That's because it's part of A2 bar.
So A2 bar indeed involves A1.
So I see, you are right. So you mean the I didn't. You mean this one, right? So this one is not.
We just get a little bit confused about notations. X2 bar involves A1 or not.
Well, let me just look it up. I thought that X2 bar only include, or XK bar only includes the previous
Yeah.
X variable. I thought AK bar only includes the previous A variables. But they're both there.
Okay.
But I will double check right now.
So yeah, that's so I think this proof itself proves this guy, but then but we don't really need this one as long as X2 is given, X2 bar is given, something like that.
So yeah, that's on the notes from last Thursday on 6th.
Last Thursday is last week, right? Yeah.
It's the part 1 of these slides.
Right.
If you go to slide 6.
So, page 6.
Yeah. There's the overbar notation, so you see that X K bar only includes the X's, A K bar only includes.
Yeah, so this is the observed one. Yeah,
But if we could use the HK.
right.
Yeah.
That's right.
X is a function of the X and A.
But X2 is a function of A,
Yeah.
but X2 bar does not
So-
include A as a vector.
So let me actually I could be. So I think this is the main result. So this result basically says you do have A1, right? So you are right. Thank you. So we do actually we cannot really ignore this. So we do use this one. Yeah, that's good. Thank you. Yeah, right. So this one actually is A1. So that means where did I messed up? So
I think the proof of 2 is fine because it's
this one should have so okay. Well, And so see, this one is the main result, right? So this, if you look at this one carefully, so this one, and then y, right? Y is given xk and ak, a by k. So that means here we do use this one, right?
Right.
So y, so proof of 3. So I should
Yeah, there should be,
A1. But where? Oh, okay. Yeah, actually, I'm a little bit confused myself. So why we don't have A2 then? Or
Well, I think what it is, when you go to equation 2.
equation 2, okay.
Actually, just what it is, so the left side of the equation, I believe, should have a 1 in after the conditional block.
Left side?
Yeah.
Well, actually, no. So this one is just expression in terms of all potential outcomes. So we don't really involve a random variable A specifically in this joint density. While for the G formula, so the G formula is the joint density of the potential outcome and the factorization, right? Factorization of the data, and that one you should have all the basically your outcome should be conditional on your history, right? I mean, so then that means because your outcome for y, right, should use this based on this a bar k. So so equation 2 is okay. Equation 3 is correct, but so I guess the only thing we need to check is I'm sorry.
Yeah, only thing we need to check is here.
He is
I
this
think,
one, right?
6 need to conditional A2 given A2 bar.
Right. So eventually, right? Yeah. So then I guess I wonder why, where did I messed up? So you potential outcome. So if this is, if you I think I think somehow 여기 here we have something like this. Well, okay. Well, I guess we're so
in equation 6, y is turned into part the potential outcome should be independent of a2 given x1, x2 parameter. So there should be on the right side. For the condition of
okay. You mean the here?
equation 6,
Equation 6, okay.
there should be a1 right side of the condition of sign, yeah. Because this
A1, right.
The potential outcome y is turned into bar should be independent of a2 given your information next to one.
Yeah, I know. I mean, it should have. I understand. We should include A1, but I think the formula actually says that we should also include A2. That is why we are confused, right? The formula here is you have A2.
But you were writing that in terms of observed outcome, not potential, right? So this is observed one.
This is observed one,
But
right?
I think you are writing both in terms of potential outcomes.
Oh,
Both
yeah,
are
one
external.
more step,
Yeah.
six.
In equation 6, you are writing in terms of both potential outcome or external.
Right, but then later we'll use the integration to remove this potential outcome. Right? Right, okay. So I think well, okay. I think we have I will just you know, check and come back to this this Thursday, maybe. Okay, well, I think this is a little bit less rigorous, so we need to check again. I will explain further later. So let's just move on for now. Yeah. Or is it? So once you have this potential outcome, can we? No, that is actually what you want to show, right?
We just showed them.
So this is what we are kind of showing, right?
Yeah. I think if you have the condition, like the indicator function, too far, too far. I think that's.
Let's solve the problem. Okay.
Because then when you take the integration and it's conditional on A2, then you get the correct potential outcome that you observe, because you know what you actually chose at A2.
Yeah, I think should be, right? I mean, so basically we want to, what we want to show is this guy is equal to P Y star A2. I mean, the notation is a little bit star A2 given X1 and X2 A1 star, right? This is what we want to show. And so this is what we really want to show. And I'm not sure whether there seems to be we need one more step to complete the proof. But
Maybe we can just do the integration.
you mean integration of what?
The right hand side of 3 is that expression.
You mean this one?
Mm-hmm. Like with with 6 and 7 plugged in.
Okay. I see. So 6 and 7 plugged in, then, right, so actually, we want to reduce this one to this way, right? So you want to start with this and to show that this is. And basically, what we showed is this guy at, at A2 is equal to this guy give condition on X bar 2 and A1. But we still need to, and this guy, so then this event, so question is whether this event is the same as this event, right? You know what I mean? So because this is a observed one, so this is X1 and X2 and A1. And so that is actually, I see, that's actually equivalent, right? So this event, condition on this event is actually, so condition on this event is actually that means that X2 star is actually A1, X2 star A1, right? So that this event is actually equivalent. The amount of information is the same. Yeah, so there's some details I need to polish, but I haven't, I didn't. So I'll fix it a little bit and see whether I can improve the proof. Okay, thank you. So, well, G formula is powerful tool in identifying the joint density of the potential outcomes from the observed data. So that is for with respect to, so this G formula is a formula in terms of the, so this formula, right? Or this formula is a expression in terms of the potential outcome, A. And now another version of G formula is that we want to obtain the G formula for potential outcome for a fixed regime. So potential regime, but it's the same story because of fixed regime is just a function that gives the particular choice of A, right? So then you can view this as a one particular A. Okay. So then this is a potential joint density potential outcome, and then you can basically, so the first equality is just a probability theory, right? Joint density is marginal times conditional and conditional, and then each conditional can be expressed in terms of the so basically this is the G formula. This is the basic G formula. Okay. So question is whether this equality holds, right? And how different of this proof, how different this proof is from the potential outcome to the optimal regime. And it turns out that it's exactly the same, I guess. So so basically, this is the for given D, right? Given D is just the given kind of a given A, and then so the priority structure is defined in terms of A, right? I mean, and so we so And this is essentially a realization, right? One element in the support of A1. The same thing here. Well, so that is, so point is pretty much, the idea is pretty much the same. So then the general expression this is a summary of the general expression. So basically, for a given D, so the sequentially, right? Sequentially, D1 is a function of X1. D2 is a function of the X1 and the realized X2, something like that. It can be expressed as something like this. So we have a marginal density of X1, and then sequentially compute the conditional distribution. So that is a joint, but you may be only interested in the marginal potential density of the potential outcome of Y. That means you need to integrate out over all x's. Okay. So basically this is joint, right? This is a joint. And then you integrate out over all x's, so that you can only obtain the marginal Y. Okay. So that leads us to, for example, compute the value of a potential regime. I mean, for particular regime. So the idea is how you obtain the expectation from the marginal density. Basically, you will take the integration, right? Y times the integration of Y, which is, so if you do that, this guy will become a conditional expectation, and then the other thing will be the same. So it is possible to estimate, value of a regime from the observed data, which means that we can also estimate the optimal decision.
So, JP,
Yeah.
So the D only depends on the previous X.
Right.
So the treatment regime only depends on the previous
That's right.
X,
That's right.
not depend on the previous treatment. Where the previous X depends on the previous treatment,
Right.
but the regime does not directly depend on the previous treatment.
Well, actually, no, rigorously, we in the definition, right? I mean, so I think of where it does depend on the history, for example. I think that is so for example, right? History depends on X up to the decision K, and also the previous X
Right.
options.
Right. But in the derivation you just show, D is only a function of XK bar, not HK.
D is okay. Let's see. You mean
Yeah, here for example, D
right.
X bar, D
That's right. Well, that's right. I don't know why I did that. I think let me see whether the original so yeah. Yeah. So we this is identification assumptions and G computation. So here there's something like that, right?
They also
Yeah.
just define X.
Yeah. Is it?
Because
In-
this is okay, just assume that the treatments affect the future treatment only through X.
I think so. That's right. That's
So
right.
that
Right.
is
Right.
assumption.
Right. Right.
So it cannot
That's right.
involve the
Right.
case that we need to consider. some
That's
others.
that's right. I think so. Right. So I guess the in terms of the estimation of the potential outcome, whatever. Okay. So as long because even right the dependence on the previous options only plays for the observe the next one, and then once you observe it, then it doesn't really make a. I mean, if you think about I guess if you think of using a simulation, for example, to estimate it, basically we are going to sequentially simulate. So I plan to explain it soon. So for example, okay, suppose our goal is to estimate this one for a particular rule. So I have a rule. And then the identification we need some assumptions, and then we can estimate the parameter, and then so estimate the model parameter and then estimate the value. So that is basically the idea. So to do that, we first specify the model. So model specifications, we have a marginal density of x1 with the parameter c1, and then sequentially, right? Sequentially, we have a conditional model. So conditional model basically is so your decision, right? You basically your potential outcome for xk, right? So we are not really talking about the potential outcome because the G formula itself basically characterize the potential outcome already, right? So given this, you can create a relationship, and then you can do sequentially, and then you can estimate y. So that is the model. And red one means that we unknown, right? The parameters are unknown parameters. And then the likelihood function that we're gonna use is basically individually we have this observation, x bar I, a bar I, and yi. So we have an individual observation. So the individual observation can be used to compute the value of the joint density in terms of the unknown parameter, right? So basically you have a marginal density and then product of the conditional density, and then final conditional density for y as a function of an unknown parameter. and then plug in, right? And then this will be your likelihood function to maximize. The partial likelihood means that we don't, another random variable is A, right? Another random variable is A. So you could build a model for A, but we are not really. It's like this. Let me, I think it's somewhere. Here, right? So this is the data model. Your data model, this is a full data model. Your full data model has a outcome model part. And also you can have a conditional, but also there's another model for pi, right? Which is the propensity model. So this propensity model was completely ignored for our approach here, right? So we are not really making any modeling assumptions for the propensity scores at all. We just use outcome model. So that's why we call it partial likelihood. Okay. Because yeah, because we are not really interested in estimating that part in this approach. And then once you use this partial likelihood to optimize, then you can, you are now in a position to express your parameter, final parameter, which is you can. So there's two parameters essentially, right? One is the model parameter, right? Model parameter in your model, right? In your model, and another parameter is the causal inference parameter. Right? This is the parameter that you are interested in. Finally, you are interested in this particular parameter. So then this parameter, so then this C hat is essentially plays the role of the estimated noises parameter, right? You have a parameter of interest, but to compute this parameter, you need to estimate the model parameter from the sample. So that's basically the same structure as the missing data problem. But anyway, so that is, and then now you, under the model, you can write it, right? You can write it as an integral form. So to the actual computation for this integration may involve Monte Carlo sampling, right? Simulation. So Monte Carlo integration could be, for example, given the parameter, right? Given the parameter, you generate x1, and then plug into x1, put it to your particular d, right? Because of the d is a function of the x values, right? So given the d, you can actually generate x. So you're right. So and then this d takes a particular value. So because it takes a particular value, you can actually compute this one already, right? As a function of x bar. So in your question, even though you must question, so basically, even though originally this k is x bar k and d bar k minus 1 originally, right? So even though this is a more rigorous expression, but this guy is a function of x bar k minus 1. So then you can write the whole thing as a function of x bar k, right? This is just another. So this function is not exactly the same function, but this is just as a function. This is a function, right? So that's in that sense you can write this way. So end of the day, you can basically do simulation sequentially, right? So generate x1, generate x2, generate xk, and then plug in to generate Y. And but remember because you have a specific D, right? Because you have a specific D, basically this D gives a different choice of the path, right? And so that actually gives you a kind of a Monte Carlo sample. So this Monte Carlo sample is basically give the right amount of the probability of all the possible passes, so that you can average them in the end. Okay. So that's a completely simulation-based approach. One thing I can say that, you know, your baseline sample, you don't need a model actually, because you can use observation, right? You observe X1 throughout the sample. So you, instead of making a parametric model, you can basically use the amplitude. So you can basically simulate. You don't have to simulate X1. Because you know X1 already, right? So given for each unit, you know X1. So use that particular X1 to generate X2. And that's, so you can actually repeat the simulation not from the first step, but from the second step through this, right? So that way you can actually maybe do better. So that's basically the first remark. So this is a very nice idea, but the computation is burden computationally very heavy, right? So in the book, the Chattis book, they says that it's never used in practice, but I think. So I found another book by James Robbins. He has a in his book on the causal inference, he has a lot of emphasis on G computation. Let me see if I have a. Oops. I can show you quickly. Why not? What's the day? Sorry. Maybe I will just give the link to the announcement. Okay. By the way, so this is already 12th week. So so this week we'll finish chapter 5, and then 13 and 14 should be able to finish chapter 6. And that's it. So we are done with the DTR. And then, so that will be end of the April. And then hopefully we'll have some final presentation in the first week of May. So that will wrap up our semester. Because the book, so chapter 7 is a survivor. So I don't think I can cover survivor topic. So for DTR, at least the DTR, the main ideas of DTR will be fully covered up to by the end of chapter 6. So yeah.
The G formulation essentially is meaning just identified by using the conditional.
Right.
Sequential way.
Right, sequential way. Right.
So why it's not called S?
Huh?
Why it's not called S formulation or whatever? Why it's called G? Because if you think of sequential or conditional, so it should be called S formulation or C formulation. Why it's called G formulation?
I see. Right. So why call it G? Right. Yeah. I'm actually curious. He should have an answer. I think he has an interview at some seminar. There's some story behind. I will check. Yeah, that's interesting. Why this is called the G? I no idea. Huh? Yeah, well, we'll see. I don't know exactly. By the way, his paper. So if you look at the paper, so this is the first paper ever, dealing with this problem. Look at the page number. How many pages? Yeah, 100, almost 20, right? I mean, pages, a single journal paper. It's crazy. Anyway, yeah. So he has everything in one paper, and then he basically all the others are just explanation of his idea. Okay. So nonetheless, the G computation approach seems to be have a very good research potential, I think. So basically the potential outcomes are sequentially estimated and then combined to obtain the final simulation outcomes of Y star D on the given D, right? Okay. So here's a toy example. So you have a two decision, right? You have a two time as x1. So potential, you have a baseline x1, and then how many random variables? We are actually thinking of two potential outcome for x2, and then four potential outcome for y star. Okay, but you do observe these five random variables. So x1, x2, a1, a2, y. So basically, the homework problem is how to actually you guys can practice how you actually solve all the parameters from the toy example. So then this is basically the G formula, right? So this is the G formula. So your potential outcome probability for A1, A2 equal to 1 or A2 0 is basically can be completely determined your observed conditional probability of x2 given x1 and a1 equal to a1, right? Same way you have this. So you basically have a two decisions, right? A1 and A2, so that you can have a four potential outcome. So then the decision would be something like this. You basically have this. So you have a two decision function. D1 x1, D2 is a history of x1 and the other. So you could make it something like this. So given D, we can sequentially simulate x2 star and y star, D1 and D2 to estimate the value of the potential. So which is the potential outcome of the y star, expected value of the potential outcome of y star. So it is equivalent to imputing the potential outcomes and computing the observed imputed estimate of mean of y. Well, I plan to, yeah. So this, well, so right, because each individual only visit only one of the paths, right? Only one path, and then conceptually, the imputation would be what would be the other, right, choices? What would be the other outcomes on the different choice, right? And then once you can create the imputation, then you can conceptually compute everything, right? So that is the conceptually the idea. But there's some interesting caveat that I like to point out sometime.
So this simulation approach does not need to use the response model in the data.
Right. That's right. So remember the Q learning. I mean, so remember in the single potential outcome of how there's a three approaches, right? The outcome model approach, and then propensity score approach, and then augmented. So basically IPW approach, and then augmented IPW approach. So the G computation here is only this approach, outcome model approach. So this Thursday I plan to cover these two topics. So okay, and so if they are all categorical with category, then basically so this D1 and D2 takes the one of the values in A1 and A2, right? So basically you have an indicator function, right? So your indicator function for given A1 and A2, right? I mean A1, so for each A1 and for each pass, A1, A2, but you have, this is a kind of a region, right? Regime for this choice. And then basically your original potential outcome is expressed in terms of the A's, right? So that's why you can write this way. But the actual computation of this expectation, right? The actual computation of the expectation for categorical Y can be written as a summation, right? And so this summation, you can basically see that you are kind of doing sequentially conditional expectation. So this is a marginal expectation, marginal probability of X1, and then conditional probability and this conditional probability, right? And then you combine. I think I have one more thing. Oh, okay, right. So because the expectation for binary Y is a probability. So that's why we have a probability here. Right? So then it becomes a expectation. Okay. So this is essentially the homework problem. So you guys can check using the homework toy example. So that's all for today. We'll continue this Thursday. Any question? No. Okay, good.